Welcome back in the name of Allah. So we are now in the new glance of the intelligent sensing and remote sensing course. Here we are starting the remote sensing products, the fourth lecture, or which is the first lecture of the remotely sensed products. It is remotely sensed data. So we are starting this new lecture, which is composed of 18 slides, and it's more discussing about how we can extract the information from the electromagnetic bounce back signals. So this lecture is mainly talking about this whole stuff. Lecture 4, remotely sensed data from radiation to data. So remote sensing data starts from the electromagnetic radiation traveling from the target to the sensor. The sensor measures the physical properties of that wave and converts them into data. We already discussed that the electromagnetic source is the sun, and the sun is using the atmosphere as a carrier or information carrier to hit the surface, land surface, or the object on the earth. Based on that, when the signal is bounced back to the satellites, we are capturing the signal. This is the overall idea in which is the propagation chain of the radiation to data and how it works. Already we have seen that the sensor measure the physical properties of that wave, the wave which is back bounced to the sensor. So here's a sample formula. In this formula, if you see, the key measurement quantity is usually at the sensor radiance. We have seen that also we are actually capturing from the wave its radiance or intensity, not its reflectance. After certain processing, we are deriving the reflectance from the radiance. So in this formula, LS equals to the d square pi divided by the dA times d sigma times cos theta. So in this case, the LS is nothing. It is at the sensor radiance. I mean, they are checking or measuring the radiance at the sensors. And if we see, the pi is the radiant flux and A is is the sensor area, and sigma is a solid angle, and in the theta is the incident angle. So all of these are combined. We are measuring the radiance at the sensor. In this lecture, the important idea is the remote sensing sensors do not directly see the objects. I mean, this is one of the main base conception also, that the from such a high distance or altitude, how the sensor can see the visual objects or visualize the objects on the earth. They measure the radiance coming from the object. We discussed that everything have its own spectral reflectance. Based on that spectral reflectance in the bounce back the electromagnetic waves is actually captured by the sensor, and from that they are deriving all this information. So this is idea from the radiation to the data. What is multiple band acquisition? Multiple band acquisition, the incoming electromagnetic signal can be separated into the different spectral components. Already we discussed the spectral, multispectral sensor and hyperspectral sensors. The multiple spectral sensors are collecting a few bands of data, like from starting from 4 to 5 bands, and the hyperspectral bands we are collecting starting from 10 bands to the 100 bands, which is very nano band, having a very nano bandwidth like 2 to 5 nanometer. And in the multiple spectral sensor, we have seen that the bandwidth between the bands is like 100 nanometer, starting from 9 to 100 nanometer. So the multi-band acquisition exactly reflecting those sensors. Its acquisition has been happening by those sensors. The incoming electromagnetic sensor signal can be separated into the different spectral components or bands. How this is separated into the different spectral components or the bands, it is actually based on the wavelength. The wavelength which is coming based on the multiple intensities or the continuous intensities capturing by the sensor, they are taking the multiple bands. So each band measure radiation at a specific wavelength range. As I said, that they are see the incoming, the bounce back radiation magnetic wave, and looking into that in the multiple wavelength, and they are capturing, and based on that capturing, they are making them as in one band of it. So simple example is a multispectral satellites may measure blue, green, red, near infrared, and shortwave infrared separately. So this is how the multi-band acquisition works. So they are capturing the blue, green, red, near infrared, and the shortwave infrared separately. That's why we said in the multi-band acquisition, special example of the multispectral satellites, they are capturing 4 to 5 bands, and all the bands are starting from the visible part in near infrared and shortwave infrared, and they are capturing everyone as a separately, and it's just due to the specific wavelength range. The key idea here is a single pixel can contain multiple values, one value for each spectral band. This is the normal. So we will see more the multiple bands acquisition in detail. What is actually we are measuring from a wave? So far we have seen already we are capturing the radiance from it. For each spectral component, a sensor may measure multiple things, but in the Sentinel-2 case or the classical satellite, we are mainly observing the radiance or intensity. So from the sensor perspective, if we see we are capturing or measuring multiple things from the wave, so starting from the amplitude or the power, this is the most common in the optical remote sensing. The second one is phase, very important in SAR in interferometry. SAR is synthetical aperture radar. So we are capturing amplitude and power phase. And the third is polarization. As we discussed that the electromagnetic has a polarization, and it is the sidewise variation or oscillation of a signal, even capturing the polarization of the electromagnetic waves. So important in radar or polarimetric sensing. And the fourth one is frequency or wavelength, which is really important in the classical satellites, usually used as a band reference. So based on the frequency in the wavelength, we are actually using as a reference for the bands collections. But in the optical remote sensing, as I said, in the classical remote sensing or optical remote sensing is mainly Sentinel-2, the main measured information is usually radiance or intensity. It is exactly the same amplitude or power, not the phase or nor polarization. We are not capturing in the optical remote sensing phase or polarization. So the main thing is amplitude and multiple frequency and a wavelength. Now, what is the main difference between the optical remote sensing and microwave sensing? Optical remote sensing works differently uh, in comparisons to the microwave remote sensing. Optical remote sensing is measuring incoming radiance, which is the reflected or bounce back electromagnetic waves from the land surface. Reflectance is later estimated from radiance. So far, we have discussed this multiple times. It is highly directional. We have seen that the one of the radiometric term, it was called in the first lecture by the name of the um, radiance. Radiance is direction aware. So that's why we are capturing a radiance, not the polarization, not the phase. So it is highly directional, and phase and polarization are usually not measured because sunlight behaves chaotically as a reference. So this is the reason why we are not capturing of the polarization in phase, that the sunlight behaves chaotically as a reference. But in the microwave remote sensing, often uses phase and polarization. They are actually capturing the phase and polarization, important for the radar, SR, synthetic aperture radars, and interferometry. We have seen already this, treated separately in more advanced courses. So the objective for this course, it is we are discussing the optical remote sensing. We are measuring the radiance, and later on we are deriving the reflectance from it, and it's highly directional. And why we are not capturing polarization in phase, it is the sunlight behaviors chaotically as a reference. We have seen the multi-bands acquisition. So what is bands in multi-bands pixels now? We have seen that for the any one band, we have a single value pixel values. if you see here that a single pixel can contain multiple values. A single pixel can contain multiple values, one value for each spectral band. This is one of the key idea, and that's why I gone back to there. Now we would like to see bands by itself and the multi-band pixels. So pixel is a small unit of the picture actually, but in the context of the bands, we would like to see more in detail. A remote sensing pixel is not always just a one number. We have seen it is a one number per pixel before for each band. For multispectral data, each pixel contains several bands value. Now, as we are discussing the multi-bands value, definitely the for each band we have a single value, so it's not now anymore one number for multiple data. So each pixel can contain several bands values. So for a certain point on a certain acquisition, a certain band, let's suppose in a one specific point and a specific condition, the first value of the pixel can be different from the second one. It is just due to the wavelength ranges. So let's suppose pixel is equals to B1 and is the value of the pixel in the band 1 and the B2 have a different B3 dot dot until the BM. So an image is like a 3D data cube in this case. It's more like a 3D data cube. So in the x direction, if you divide them by the graph or the if you see in the XY graph, so in the x direction we are having the images columns, and this is the all of the images columns are located on the x direction. In the y direction, we are looking into the images rows actually. It is goes inside like this. So in the spectral direction, they are showing the multiple bands. This is how the bands and multi-bands are located in terms of the pixels. So the key idea, remote sensing images are stored as a numerical matrices, not just pictures. This is also one of the main differentiation we have discussed in the remote sensing instruments of the imagery and non-imagery radars, that the imagery radars can penetrate the cloud, so they are uh, directly output you as an image, but in the non-imagery like LiDAR in other we have seen they are not providing you direct in a picture, or they are also providing you a numerical matrices, not just a picture. In the previous of the slide of the multi-band acquisition, they said that a single pixel can contain multiple values. This multiple values is basically coming due to the multiple bands, because this is the multiple band. So one value for each spectral band. On a one band, they have one value, but if you are changing the band due to the wavelength and ranges, so they will definitely change its value. So that's why they say one value for spectral band, and the value can be changed upon the bands. The more bands, the more values you will have. We discussed this one, and the remote sensing images are not stored again as a numerical matrices. It not just as a not just a picture. So later on, these numerical matrices are converted into the gray levels or into the band depth. We will discuss the band depth more in detail. Raster grade, remote sensing data is usually arranged as a raster grade. So raster is really important unit in the remote sensing data, and is usually arranged a raster grade. What is raster grade? A raster grade is a rectangular matrix of pixels. It is a rectangular shape of pixels. So the unit of the grade, raster grade, is still the pixel, and it is the shape of the rectangular. Each pixel correspond. This is exactly the same of the pictures as given in the right side. So this is the one band, two bands, three bands, multiple bands in the k direction. On the axis, we have the images collection. In the y direction, we are having the rows of the images. So this is how a grid can be represented, is the shape. And I also touch giving you the bands and multi-bands pixels. In the previous slide, we have seen exactly the same in this way also. So a raster is a rectangular matrix of pixel. Each pixels correspond to a ground area and contains one or more values depending on the number of bands. We have already seen that the number of the values are depending on the bands. So each pixel summarizes the signal from a small ground area. So they are the summarization of this small ground area from the a certain signal. So this is called raster grid. So raster grid is a rectangular matrix of pixel in short, and each pixel correspond to a ground area. The acquisition they have taken, it contains one or more values depending on the number of bands. One of the core concept of the this lecture of the remotely sensed data, it is the resolution, and we'll be more focusing on the resolution throughout the remaining slides. This is the core concept. Resolution is one of the most important concepts in this lecture. General definition is the resolution is the smallest changes in its measured quantity that produce a detectable changes in the instrument reading. The instrument reading is basically a sensor, so it is the quantity which produce a detectable changes. A detectable changes in terms of the multiple spectral resolution, spatial or geometric resolution, radiometric resolution, and temporal resolution. So resolution is more about the finer details. So all of these are the types of the resolutions which can affect the or the measurement instrument while producing the resolutions of the acquisition. So this is called resolution, and we have in remote sensing multiple types of resolution. The first one is spectral resolution. Spectral resolution is about the wavelength, and it is the reflectance of the objects. The second one is spatial or geometric, so it's more about the location in of the object size. Radiometric is the intensity and amplitude. This is also important aspect of the resolution, how much the signal is strong. And the temporal resolution is about the time and revisit. So this is the core concept. Now we will discuss each type spectral in details, higher, lower spectral resolution, spatial, each and everything, and detail. Starting with the first one, the spectral resolution. We already know about the spectral. It is more wavelength dependent or lambda dependent. So it is basically depend on the wavelength. So the more wavelength is shorter, the more the spectral resolution will be. So spectral resolution means the ability to distinguish between the different wavelengths. So we have again multiple types of the spectral resolution. We have seen the multiple bands. So we are starting from the monospectral, means one band, multispectrals, several bands, several broad bands. So multispectral bands is starting from 4 to 5 bands. And then we have a hyperspectral bands, many narrow bands. We have already seen the hyperspectral band sensors, which is basically capturing from the starting of the 10 to 100 bands, and which is very narrow, like 2 to 5 or 3 or 4 nanometers, and they are having a more details on the oxygen level. So the ultraspectral is very many narrow bands, even more than from the hyper, like you can assume like 1 or 2 nanometer. The higher spectral resolution gives them more detailed materials, but it's also create a more data. Like it is associated definitely because the bands they are generating, so they will definitely generate in petabyte data. Definitely the cost will be higher and more processing difficulty. Yeah, of course, for the processing, the computation power is required. More bands do not always mean better performance. More bands do not always mean better performance. This is linked to the a huge phenomena with too many features with limited training data can reduce the classification accuracy. This is one of the important aspect in terms of the always, it's not always better performance. Like if we have a more bands, do not always means that is the better performance. This is exactly linked to the classification accuracy, how accurately it is classified during the processing. So it is also important phenomena to understand in the spectral resolution if we are going towards the multiple or the hyper or the ultra spectral bands. It doesn't mean the higher resolution. This was one of the example or the type of the resolution we have seen. Now we have the spatial or the geometric resolution, which is another one important type of the resolution. This is more talking about the object and the size and location. Spatial resolution describes the smallest object or a spatial detail that can be observed. So they are looking for the smallest details about the object. In practice, it is often related to pixel size. Exactly. This is more about the pixel size, about the captured acquisition of the signal. So it starts from the 8 meters resolution. It is less detailed. But if it is a 1 meter resolution, it means a more details. The smaller the pixel size usually means better visible details. As we are smalling the pixel size, so it means more details, but not always better analysis. We have seen this, the analysis point in the case of the spectral resolution. It depends upon the classification accuracy while processing such a huge amount of data, which really associate the cost, storage, and processing information. The same case applies to here. Like it is not necessary if we have the smaller pixel size and it means the better is the detail. Usually it means better details, but it's not always good for the better analysis for because the ultimate objective from the search acquisition in clear quality is the analysis, and the reason is the processing of such data. So let's move on in detail explanation about the spatial or geometric resolution. We have two important terms. One of them is called GIFOV, and the second one is GSD. So GIFOV stands for the ground instantaneous field of view. It is mean as exactly like ground area summarizing by one sensor measurement. The follow-up version of the GIFV is the GASD. This is the ground sampling distance. And both of them are almost the same. Distance between the neighboring pixel centers. This is making as a reference the neighboring pixel as a center. Usually GIFOV and GSD are similar, but they are not always exactly the same. So there is a chance to be different. No spatial details smaller than the GIFOV can be directly observed. That's one of the important aspect because the GIFOV is the ground instantaneous field. Instantaneous field, I mean the minimalistic view of they can observe. If it is decreasing more from the GIFOV, it cannot be directly observed. It can be directly observed. No spatial details smaller than the spatial details smaller than the GIFOV can be directly observed. So, I mean, there is a chance we are losing the spatial information, which is smaller than the GIFV size, the ground instantaneous field of view. Although it may sometimes be inferred indirectly. So there is the chances that can be inferred indirectly. But the case, these are the two terminologies we have seen. It's also relevant to the resolution. So those spatial information, which is smaller than the GIFOV, it cannot be directly observed because the ground instantaneous field of view is the smallest view of the objects on the Earth. Lowers is a high spatial resolution. It is again relevant to the same resolution concept, but it's not a type of the resolution. Or you can consider the side aspect of the resolution. We should have to know about it. Low resolution mean pixels are much larger than the objects of interest, which is we are in favor of this case. We have seen in the spatial resolution the same case. If we see, the smaller the pixel size usually means the pixel size is smaller means actually this is smaller from the object size. So that's why they are providing the better visible details, but that's not the case for always the better analysis. The same applies here. The low spatial resolution, the idea is the pixels are much larger than the object of interest here. This is exactly the low spatial resolution. Here the pixel is larger than the object of interest. So that's why the spatial information is now not much visible. The spatial information is most about the object size and the location. So results are happening. Each pixel contains mixed materials. That's why I mean, if we are doing in the length cover analysis, we can see that the two area can be or interoperating or overlapping each other. Spectral information dominates here because in this case, the pixels are larger than the object size. So spectral reflectance can appear responsible, be much more dominant, but this is useful for large scale patterns. This low spatial resolution where we would like spectral informations to be dominant. But if you see in the higher spatial resolution, the pixel are now smaller than this is exactly the case we have seen in the spatial resolution type of the resolutions. So here the pixel is now smaller. So if the pixel is smaller from the object on the earth, so it means the quality is automatically better. So result is the spatial patterns dominates here. So we are looking actually to the object size, the location, each and everything with texture, morphological information, topological information, all of these things, and geometric attributes. Individual pixel may not be meaningful alone. Yeah, that is one of aspect we should have to take into the notice, that the individual pixel may not be meaningful in alone. Object, shape, texture, and context become important here in this case, because we are going towards the analysis. And here the spectral information is not dominating. Here the spatial information is dominating. The key idea, at the low resolution, we classify mainly by spectral response. I mean, when we are at a low resolution, this is mainly classified by the spectral response. At a high resolution, we often need a spatial information in object context. This is how we are differentiating the low resolution and the high resolution. So low resolution is the classified by the spectral response. If the spectral response is dominating, we say there is no spatial information, or the spatial information is overridden by this spectral response. But at high resolution, we often need the spatial information in the object context. So here we are say the spectral response is decreased or de-dominated. This is the whole idea about the low and high spatial resolution. Now we're discussing the spatial information. Okay, we understood about the spatial resolution or geometric resolution. Now, that was the type of the resolution. What is exactly the spatial information mean? So spatial information means more than just a pixel coordinates. So now here we are discussing step by step the spatial information, why it's not just a pixel coordinates about the land cover or object or the target. So it can include the geometric attributes. What is exactly geometric attributes? We will see the textural attributes, topological attributes, and the contextual attributes. So these are the three the spatial informations which are given to us by the spatial information in addition to the pixel coordinates. Now, what is exactly geometric attributes? They are including shape and morphology. In the shape and morphology, we can see such as the area, parametry, compactness, linearity. And if we take the example, distinguishing a round forest patch from a rectangular agriculture field. So by distinguishing these two, it is really easy and helping us. They will be really helpful, the geometric attributes of the spatial information to distinguish the rough forest patch from the rectangular agriculture field. Or you can take any football or the cricket stadium example. It will be really easy to differentiate it by using by the higher spatial information we have seen. In that case, the pixel values are lower than the object size, so it means the spatial information is dominating here. If we see the texture information in the geometric, we have seen the shape in morphology, and there are the area, parameter, and compactness and linearity. But in the texture attributes, we are looking the roughness or variation of the pixel values. This is now really important. The example is distinguishing a smooth paved road from a rough grave path. This is exactly helping now the texture. Even from the spatial resolution, we are deriving the texture attributes, which is exactly the local roughness or variation of pixel values, which are helping us to differentiate between the smooth paved road from a gravel path. So even to the texture level information, we are analyzing with the spatial resolution. The third one is topological or contextual attributes. They are including the spatial information, three types of attributes: geometric, texture attributes, and the topological or contextual. In the topological or contextual attributes, it is more talking about like the neighboring effect or regency effect. The spatial relationships such as the proximity, adjacency, hierarchy, examples of a swimming pool as usually or often near in a house. So if you take in this example, it can affect or it can be overlapped with each other in the spectral response, where the pixel values are smaller, larger than the object size. So very important idea. In a pixel, in this topological or contextual attributes are helping us to distinguish between the adjacency and the hierarchy in the proximity objects of each other. And this is really important in spatial information from the sensor, the sensor resolution of the spatial resolution. A very important idea, a pixel meanings is not always inside the pixel itself. It may depends on its neighborhood. This is exactly relevant to the topological and contextual attribute. In the contextual attribute, it's not always necessary what we are looking at in terms of the pixel. It is itself inside the pixel, but it may also depend the effect of the neighborhood or adjacency or the hierarchy. Like in the example of the swimming pool, we know it is often near to a house. So I mean, if you are looking especially to the house, spatial information from the topological or contextual contributes attributes, so they can be easily differentiated or distinguished based on the this thing. And there is a chance in the spectral information we can see overlap by each other. This is the spatial information. We have seen the resolution. In the resolution, we have seen two types so far, the spectral resolution and the spatial or geometric resolution. This is the spectral resolution. We have seen the spatial resolution. There are two terminologies, GIFOV and GSD. And we have seen what is low and versus high spatial resolutions, what is the role of the pixel, and how each or both of them are dominating on each other, spectral and spatial. And then we have seen what is exactly spatial information and which attributes are contributing to the spatial information. We have now pixel-based versus object-based analysis. How we should look to the objects. It can be analyzed based on the two methods, pixel-based or the object-based. So traditional pixel-based analysis treats spatial information mainly as a coordinates. And this is the traditional pixel-based analysis of the X and Y. But in the geographic object-based image analysis, which is GEOBIA, is uses the object, shapes, texture in context. And this is exactly the same spatial information they are using. Spatial information are using by the geographic object image analysis, object-based image analysis. They are using the shape. The shape is exactly the geometric attributes of the spatial information. Texture is exactly the texture attributes, and the context is the topological or contextual attributes. Based on these spatial information, the object-based analysis are happening, but in the pixel-based, we are treating them, the pixel-based analysis treats spatial information as an mainly coordinates of X and Y. So in the key differences, the pixel-based analysis, individual pixel or spectral values, individual pixels are representing an spectral values, but in the object-based analysis or GEOBIA, which is the geographic object-based image analysis, they are using the groups of pixels, shape, texture, and context. This is the main difference between the pixel-based analysis and the object-based analysis, and how we can differentiate them. And that's why the spatial information is really helping now. And they are grouping them in the image object-based analysis or the image-based analysis of the pixels, shapes, texture, or context. But in the pixel-based analysis, it is more like they are treating the spatial information as a coordinates of X and Y. Now this is the another important radiometric resolution. This is now the third one, resolution. And what is the quantization? As we know from the radiometric resolution, here we are capturing the sensor. Sensor is trying to capture the electromagnetic wave, radiometric. So radiometric resolution is about how finely the sensor can distinguish the differences in the intensity radiance. We are capturing mainly in the optical remote sensing the radiance or the intensity of the electromagnetic wave. So we have seen in the start, we are also capturing more things like phase, amplitude, and the polarization, and the frequency and wavelength. But in the optical remote sensing, we are mainly discussing the intensity and radiance. So this intensity and radiance in the radiometric resolution, they say how fine the sensor can distinguish the difference between the intensity and the radiance. The sensor measures a continuous radiance values continuous because the electromagnetic waves are continuously bouncing back to the sensor and they are capturing, so it is a continuous set of values of the radiance or intensity. But how the system is storing, the system stored this as in a discrete numbers, called them the digital number or DN. In the conversion process from the continuous values or radiance values into the digital numbers or a discrete numbers, it's called quantization. In the quantization is converting continuous values into the finite discrete values and saved in the system. Quantization introduce an error at the same time. So EQ equals to the LQ minus LI. So LI is the measured input radiance and LQ is the quantized input radiance. So this is really important in the radiometric. They are mainly talking about how finely the sensor can distinguish the differences from the captured intensity and the radiance in measuring with the total intensity, which is the total intensity coming from the electromagnetic source, which can be distinguished by multiple or captured by multiple source of the sun positions, inclination, and the orbit in multiple aspects. So we are comparing them in the radiometric, and then when they compare with the total intensity and the capture intensity, so it becomes a continuous number. But when we would like to save them in the computer, it cannot be saved as a continuous value, but it should be a discrete number, like we can call them a digit number. And the conversion process is called from the continuous radiance values into the digital number is called quantization. And they can also introduce an error. We have seen the error is EQ equals to LQ minus LI, which is the measure input radiance minus the quantized input radiance. Now this is the bits in the digital numbers, which is again really important. We have seen that the bit depth is already important. The normal depth is using the in the Earth observation, that is from the 8 to the 16 bits, but the formula is the number of possible digital value is to the power n. So if we have 8 bits is 256 and so on, and 10 bit it is 10,024 values, and the 16 bit is over 65,000. In the radiometric step, if we see it is LSB. LSB is least significant bit, and we are dividing them by the smallest radiometric. Smallest radiometric step FS is a full scale and divide by 2 to the power NB number of bits. So the key idea here, the higher the bit means the finer radiometric discrimination. Why it's really important? Because let's suppose if we have the bit depth of the 16 bits, and if we compare with 8 bit of the depth, which is 256 values, so the 16 bit depth is much better, and they can really help us define a radiometric discrimination. The signal they captured is very clear. They can differentiate between the shadows, the colors, and more bright and illuminated the object will be. So this is the idea. The higher the bit depth, define that the radiometric discrimination will be. Temporal resolution, which is the fourth one resolution type, and we are looking into the temporal resolution. Temporal resolution is the time needed to acquire the fresh data over the same location. This is a really important concept, and we have seen already the temporal resolution before a little bit a touch. So temporal, what does mean by the word temporal? It's as from the name obvious time. So temporal resolution is important, and it is the case we are analyzing the data in multiple time frames. So the temporal resolution is the time needed to acquire the fresh data over the same location. The same location is dependent, okay? Coverage frequency, if you remember from the second lecture, I think so. From the second lecture, coverage frequency and coverage frequency coverage. One of them was the frequency and one of them was the frequency coverage. In the one of them, the area is the broader. It's not necessary to be the same area, but with the same conditions. Area can be the same, but condition can be different. but in the frequency coverage, it should be the same conditions. So that's why the temporal information help us in the cloud-free acquisitions. We are looking to the floods, oil spills, plant diseases monitoring, vegetation phenologies, and change reduction in trend analysis. If we are looking into the climate changes, so the temporal resolution is really helping us, and there are multiple classifications of a high, medium, and low, and the time is dependent. In the high it is less than 3 days, and the medium is 4 to 16 days, and the low it is a more than 16 days. So when we are capturing the temporal resolution, and then we are looking to the change reduction in the trend analysis, and it can be depend upon the application where we would like to use them. Multitemporal versus temporal, hypertemporal data, it is the same concept relevant to that one. As we know from the multiple spectral and multiple spectral sensor or multiple spectral resolutions in the same hyperspectral sensor in the hyperspectral resolutions. So these are the names exactly. Multi or hyper is added to the temporal. So the multiple temporal data set, let's suppose we have acquired the multiple temporal data set, and the multiple data temporal data set can be now depend which one classification is that one. If it is in case on a high, we are assuming in the high case. In the high case, data acquired in the different dates. So different dates could be like three less than the 3 days. Okay. In the hypertemporal data set, very frequent time sampling. Very frequent means less than, it's a more than a high. So what are the benefits of the multiple temporal versus the hypertemporal data? And the multiple temporal data is useful for the change detection. We have seen that the effect or the benefits of the importance of the temporal resolution is one of them is the change reduction. But the hypertemporal data is useful for fast changing phenomena. It is more than, that's why I said in the hypertemporal data sets, the meaning is the very frequent sampling. It means that time is less than the 3 days we have acquired such data. Now, all of these resolutions are the trade-off. It is the trade-offs we are deciding. This is one of the important final idea that the remote sensing resolutions compares with each others. Involving improving one resolution may reduce another or increase the cost. So we are taking the cost. If we are increasing the one another will be decreased. So this is the possible four trade-offs. If we are looking to the higher spectral resolution, we will be definitely having a higher amount of data in petabytes, but lower signal to noise SNR ratio. The lower the signal to noise ratio means the lower the lower the signal is captured. The captured signal or the captured electromagnetic wave is very weak. But if you see to the higher spatial resolution, here we have already seen in the higher spatial resolution or lower spatial resolution, obviously the pixel size is smaller than the object size, so less collected energy per pixel. Here the per pixel energy is very less. In the higher temporal resolution may require wider swath or a lower spatial detail. If we increasing the higher temporal resolution in case of multi-temporal data or hypertemporal data, so we need to increase the width of the swath. Width of the swath, we discussed the swath is the stripe of the acquisition, and width of the swath is the width of the stripe. So we need to increase that wider swath or lower spatial details. So automatically, if you are increasing, so you need to increase the, if you need a higher temporal data, so it is automatically that they require the wider swath, but lower spatial detail will be captured in this case, because we are more focusing on the temporal information and they are losing the spatial information. In the higher radiometric quality, we discussed that we are mostly interested about the capturing of the signal. They need a stronger signal in a better sensor. Here the cost can be increased automatically, so in the radiometric quality, and this can also happening in the quantization process after the continuous, we have seen continuous radiance values and then converting into the digital number was the quantization process. So they definitely need the stronger signal. If the signal is not stronger, so it cannot be helpful. Also, in the cost is useless. We used a better sensor. So this is maybe in the high radiometric quality, we can, if you're using this sensor in the low Earth observation, so it can be more lower to the closer to the Earth for capturing the single signal more better. But it depends upon the application. Signal to noise ratio or SNR is limiting the remote sensing data quality. This is one of the important aspect. And the higher SNRs means better data definitely, but it's not free. I mean, we are paying some cost for it, like refining the resolution, usually decreasing the SNR. Signal to noise ratio is one of the important aspect we need to consider in the trade-offs of the resolution. So if we are increasing the spectral information, we are losing the spatial. If we are dominating the spatial, we are losing the spectral. And if we are looking for the temporal information, we are losing again the spatial and need a wider sweat and the higher radiometric quality. In that case, we need a better sensor and better signals to capture. So this is all about the fourth lecture, which was the start of the remote sensing products. It was remotely sensed data. We have seen the resolution, how the data are captured, multiple types of the resolutions. This is all. See you in the next lecture. It's about the data formats and visualization. That will be the fifth lecture of the remote sensing. Bye.